Let's start. Okay, good afternoon to all the participants who have joined in, and hello to those who will be viewing this later. So, as part of your Advanced Materials Chemistry course, from today onwards, we are starting the subsection which is your functional materials. So, functional materials, as you all know, are materials which are tailor-made to perform certain functions. And under this subsection, there are a few materials which we will be covering in this particular course, and they are energy materials, and also you have magnetic materials. So in energy materials, for today as well as the coming class, what we will be covering is batteries and supercapacitors. So in batteries and supercapacitors, this particular lecture 1, which I will be covering today, we will be covering a little bit basics of electrochemistry. Then we'll be discussing a little bit of batteries, primary and secondary batteries. Then what energy and power density means in terms of battery. Then we will discuss the nitty-gritty of lithium-ion battery, then components and processes in the batteries, and also a little bit detailed about cathode materials, which we will consider for lithium-ion battery. So why basics of electrochemistry? Because many of you will be coming in from varied background, and before we actually talk about energy materials per se, energy storage materials based on electrochemistry, we need to revise a little bit about our electrochemistry basics. So we'll cover a little bit of history. Nothing in electrochemistry can start without discussing a little bit about Alexander Dutta, who announced his invention of the voltaic pile, which was the first modern electrical battery in 1800. So a good solid 200 years ago, almost 220 years ago, the story of electrochemistry began when the voltaic pile was kind of made by Alexander Volta. So the two metals which Volta used to build the pile were zinc and copper. And what he did is, in between the zinc and copper discs, he put in a pasteboard or a cloth which was dampened with brine, which is nothing but a solution of water with salt or vinegar. And the electrochemical reaction on each of these 3-disc unit of the pile, it formed an electric cell and it generated a current. So as you keep on changing the number of units, you could increase or decrease the amount of the electricity which was produced. Now, using this voltaic pile, later on, William Nicholson and Anthony Carlisle, they used it to split water into basic components, which is hydrogen and oxygen. And this actually ushered in the era which we call, or a particular field of chemistry which we call as electrochemistry. So now this field of electrochemistry, as it started from 1800, in the last 200 years, we have seen a lot of landmark achievements which has been achieved by really brilliant minds. So few of these pioneering works, any person who is embarking on electrochemistry should know. So we'll just, kind of give you an idea about the different landmark things which were done. So one was the law of electrolysis, which was in 1833 to 1836 developed by Michael Faraday. Then we had Daniell cell in 1836 by John Frederick Daniell. Then fuel cell with William Robert Grove in 1842. Then we had the lead acid battery, which was by Gaston in 1859. Then we had electrolytic production of aluminium, which was brought about by Charles Martin Hall and Paul Herold in 1886. Then induction motor, use of AC current to drive an induction motor by the famous scientist Nikola Tesla in 1887. Then we had Arrhenius and Nernst, who gave you the idea about dependence of reaction rates on temperature and general interpretation of the thermodynamics of electrochemical process. Then we had the Cottrell equation, which is very important, which rules the relation between electrode kinetics and mass transport by diffusion. And this came in 1903. And then, of course, the nickel-ion battery by Thomas Edison in 1914. So these were all the different landmark achievements which ultimately led to the field of electrochemistry. So what exactly is electrochemistry? It is the discipline that deals with chemical reactions that involve an exchange of electric charges between two substances. So basically a chemical change which is giving rise to an electric current. So it is a study of reactions in which the charged particles, they cross the interface between two phases of matter. Typically, it's a metallic phase, which is your electrode, and then you have a conducting solution, which is your electrolyte. And we all know that when we are adding an electron, we call that process a reduction process. When we are losing electron, we call it as an oxidation process. So these are the very basic points. And a few more basic concepts which will be developed which we'll discuss is basically the electroneutrality principle. So what is the electroneutrality principle? That any bulk matter, it cannot have a chemically significant imbalance of positive as well as negative ions. So it has to be kind of neutral, electroneutral. Then suppose we are talking about the dissolution of a metal in a particular solution. But that dissolution is going to happen only to a measurable extent if you are able to remove the excess negative charge that remains. So if you have some electron acceptor ions in the solution, or you are drawing out the electrons from the metal through an external circuit, only then the dissolution of the metal is going to continue in that particular solution. Then we have something which is very important, which is known as the interfacial potentials. So these generally exist at all the phase boundaries. So if you are having a metal in contact with an electrolyte solution, then this interfacial region will consist of an electric double layer. So at that electric double layer, you will find this interfacial potential developing. And the potential difference between a metal and a solution, this is entirely located across a very thin double layer, and it generally leads to very large potential gradient across the region. So to give a view of it, if you look into it, you have this electrode potential, as you can see over here. It is given over here. You can see that as the distance from the surface of this electrode is increasing, the concentration of the cations or anions, as the case may be, decreases, and it actually gradually becomes equal to the concentration in solution. So as a result, what you're having is this electric double layer formation. So at the surface, you have a potential which is around phi 0, and at the distance x, you have something which is phi x. So ultimately, this difference in potential is nothing but your electrode potential, which is given by this particular equation, phi 0 minus phi x, giving you the electrode potential E. So in a voltaic cell, what you are doing, you know that the motion of electrons in ionic bonding, it can be used to generate an electric current. And in a voltaic cell, you're precisely doing that. So you are having two different electrodes which are made of different materials, and both of them will chemically react with the electrolyte with some kind of an ionic bonding. So what exactly happens in this case? Suppose if you're a zinc anode and you have a particular solution of your nitric acid in it, and then you have a copper cathode. What happens is basically there is a movement of the electrons from the zinc anode to the copper cathode. The flow of the electrons is always from the anode to the cathode. And this is nothing but a voltaic cell or a galvanic cell, or also this is known as the Daniell cell. As I mentioned, the invention of the Daniell cell. So in the zinc electrode, what happens? You are having that zinc is going into as zinc ions, whereas in the copper electrode, what we are having is copper ion is taking in the electrons and it is forming copper. So when you are actually looking into the electrolytic cell, after a while, if you are picking up the electrodes, it looks somewhat like this. The zinc has eroded, whereas the copper has deposited. So this is the voltaic or the galvanic cell. Then another concept which is important is the cell potential. So what is the cell potential? It is a measure of how well a cell reaction, it can push or pull electrons through a circuit. So the electrical energy generated by the spontaneous reaction, this is proportional to the cell potential. So if you are having a standard cell potential, it is given by the difference between your standard cathode potential and standard anode potential. And you can also have the Gibbs free energy, which is related to this electrode potential by the equation delta G0 is minus NFE0, where N is your number of moles of electrons, F is the Faraday constant, and E0 is the standard cell potential. But this value, if you see, of the electrode potential, it depends on quite many factors, which is the material of the electrode, nature of solvent, then temperature, concentration of the electrode material. So whenever we talk about an E cell, then we have to give some reference. So we need a reference electrode. So there are quite a few reference electrodes which you will find. But in this particular class, we'll be discussing about the standard hydrogen electrode. So what is the standard hydrogen electrode? It looks somewhat like this, where you have hydrogen gas is absorbed at 1 atmosphere pressure over a platinum electrode, which is dipped at 25 degrees centigrade in 1 molar HCl. And it is a regular electron for hydrogen, and its potential is taken as the 0 volts. So normally all these particular metals and non-metals, their reduction potential is measured with reference to the standard hydrogen electrode. And the more negative the reduction potential is, the more readily that element is going to act as a reducing agent. So it itself is going to get oxidized. Another very important thing which you should always remember when you're doing electrochemistry is the Nernst equation. So we know the relationship between Gibbs free energy and equilibrium constant. So delta K0, if you know, it is minus RT ln K, where K is basically the equilibrium constant for a particular reaction. So delta G for a reaction, it also depends on the concentration. How? Because delta G is equal to delta G0 plus RT ln Q, where Q is basically your reaction quotient, which is nothing but the concentration of your product divided by the concentration of your reactants. But if you are actually substituting this delta G by E cell, then you have this particular equation where E cell is equal to E0 cell minus RT NF ln Q, which is nothing but your Nernst equation. So far what we have discussed is the voltaic cell or the Daniell cell, or which is a spontaneous reaction which goes on in the cell. Now you have another kind of cell which is known as the electrolytic cells. And here the concept is nothing that you're reversing basically the direction of the spontaneous reaction which occurs in a galvanic cell through input of electricity. So electrolysis reaction, it will generally require electrical energy to induce the reaction. So when you are actually electrolyzing the sodium chloride molten sodium chloride, what you have is the generation of liquid sodium and you have chlorine gas which is evolved. So though the direction of electron flow, this is a very important thing, in electrolytic cells, it may be reversed from the direction to what a spontaneous reaction electron flow happens in case of a galvanic cell. Remember the definition of cathode and anode, it remains the same. So the reduction, it will take place at the cathode and the oxidation will occur at the. So if I compare a galvanic and an electrolytic cell, what we have is basically the difference which is in the cell potential. So in a galvanic cell, if you see the E0 cell is plus 0.78 volt, whereas when we go to the electrolytic cell, is minus 0.78 volt. So very easily you can make out the delta G is negative over here, whereas the delta G is positive over here. And to drive this particular reaction, you need to apply some sort of energy. Okay. Excuse me. So now there is another law which you should know, which is Faraday's law. So the amount of substance consumed or which is produced in one electrode in the electrolytic cell, what we discussed, is directly proportional to the amount of electricity which will pass through that particular cell. So this particular formula is very important. W is equal to MIT by NF, where W is the mass of the substance which is deposited and M is the molecular weight of that particular substance. I is the current passed. N is basically the number of electrons which is transferred in that particular electrolytic reaction, and F is your Faraday constant, which is nothing but 96475 coulombs. So the amount of chemical change, you should remember, is proportional to the amount of current which is passed. So that is the essence of Faraday's law. Now when we come to electrochemical cell, there are a plethora of variables. So there are a lot of external variables like temperature, pressure and time. Then you have electrical variables like potential, current, the quantity of electricity which is passing. The electrode variables are there, which is the material which is used, the surface area of your electrode, the geometry of your electrode, the surface condition. Then there are various kind of mass transfer variables because there is a movement of your ions through the solution. So there is a mass transfer there. So what is the mode, whether it is diffusion, whether it is convection, whether the surface concentrations also matter. There can be adsorption at the electrode surface. So all those things play a role in actually giving you that E value of your cell. So if you see, there are a lot of things happening in the electrochemical cell when the electrolytic reaction is occurring. In the bulk solution, you have the mass transfer. Then in the electrode surface region, you have chemical reactions. You have adsorption and desorption happening. On the electrode surface, there is electron transfer which is occurring. So all these different things needs to be considered when you are talking about an E cell. So that is the reason why you will find that in an electrolytic cell, we say that E cell is there. So, but whenever we apply that voltage, the reaction doesn't start. We always have to apply a little more potential, a little more voltage. Why? Because that extra potential has to be applied to an electrode to initiate the electrode reaction in an electrochemical cell. So the difference between this equilibrium potential and the applied potential required to initiate that electrode reaction, this is known as the overpotential. So the cell overpotential is generally composed of various, different factors. So the contributions come from ohmic drop, diffusion overpotential. So what are these different overpotential things? So ohmic drop is nothing. It results between the electrodes because the electrolyte solution has a finite conductivity. Normally, what we consider that the electrolyte solution, it has an infinite conductivity, which is not the case. It has a finite conductivity. So it is always occurring between the working electrode and the reference electrode. And the contribution to polarization by this particular ohmic drop is equal to IR, where I is the current density and R, as you know, is the resistance. Then there is the contribution from activation over potential. So this generally it occurs at either one or both the electrodes, and it is the kinetic inhibition of one of the steps involved in the electrode reaction. So it can be either dissolution of the reactive ion, or it can be chemisorption of the reaction product. So activation polarization, we generally say it arises due to slow electrode reaction. So the reaction at the electrode will require an activation energy to proceed. So whatever reaction what we saw at the surface of the electrode, it also requires some kind of energy to start, and that is the activation over potential. Then you have a diffusion over potential. So this is due to the presence of concentration gradient in the vicinity of the electrode surface. The concentration of your the materials at the electrode surface, they do not stay in the equilibrium value when the reaction is occurring. So if your migration through the electric double layer is very rapid, then diffusion from the bulk of the solution towards the electrode, it is not sufficient or fast enough to replenish the ions in the double layer quickly. And so what you will result is you get is a concentration gradient. And because of this concentration gradient, you have a diffusion over potential. So that is why whenever you apply potential for an electrolytic reaction in the normal cases or in practical cases, there is always an over potential issue. So now we come to batteries. So what is battery? Battery is a device which is converting this chemical energy directly to electrical energy. And what does battery consist of? Battery consists of many voltaic cells, and each voltaic cell consists of two half cells which is connected in series by a conductive electrolyte. So you have two different half cells, you have a conductive electrolyte in between, and then you have each cell, and when many of these cells are connected together either in series form or in parallel form, then what you result is basically what you get is a battery. So batteries voltage output and current rating, they are generally determined by the elements which are used in the particular electrode, the size of the electrode, and the type of the electrolyte which is used. And depending on the type, cells generally have a nominal potential anywhere between 1.2 to 3 volts. Normally the batteries which we use generally have a potential between 1.2 to 3 volts. So now there are different kinds of battery. As I said in my introduction slide that we will be discussing primary as well as secondary batteries. Primary batteries are the use and throw ones, whereas secondary batteries are the ones which you can recharge. So a primary cell, it cannot be recharged. Why? Because the internal chemical reaction, whatever is happening to give you that particular electric energy transfer, that is basically irreversible. So that internal chemical reaction, it cannot be restored. Whereas in a secondary cell or a storage cell, it can be recharged because the chemical reaction is reversible. Normally we talk about, in battery context, we will talk about, it's a dry cell. What's a dry cell? It is not that the electrolyte is a solid electrolyte. It's basically a moist electrolyte that cannot be spilled. So we call it as a dry cell. Then you have various sealed rechargeable cells. These are secondary cells that contains a sealed electrolyte, so that cannot be refilled. You can recharge the cell, but you cannot refill the electrolyte. So there are various common type of primary cells. A few I have discussed over here. There is a carbon zinc dry cell. Then you have alkaline cells. You have zinc chloride cells, mercury cells, silver oxide cells. So how are these cells? In the carbon zinc dry cells, what you have is basically, as you can see over here, a carbon positive electrode, which is the cathode. And what you have is a zinc negative electrode, which is the anode. You have a carbon and manganese dioxide mixture, which is kind of pasted on this particular current collector. And also you have a separator and you have an electrolyte paste. And this electrolyte paste is mostly ammonium chloride and zinc chloride. So this kind of cell, it's basically a primary cell, as you can see, because the reaction will occur only once and then you cannot revert the reaction back. And the performance of this cell is generally better with intermittent operation. Then you have another type which is known as alkaline cells. The alkaline cells have different types. You have AA, you have C, you have B, and that is, as I have shown on this particular figure, this AA type or C or D is basically how the different sizes are given. So depending on their standard sizes, they have this name AA, C, D, etc. So they all have the same 1.5 volt output as carbon zinc cells, but they are much longer lasting compared to the carbon zinc cells which I discussed in the earlier slide. So it generally consists of a zinc anode and a manganese dioxide cathode in an alkaline electrolyte, and the electrolyte is generally potassium hydroxide. And it works with high efficiency when with continuous use, and this is because of the lower internal resistance this particular cells have. Then we are coming to another heavy duty type of primary cell, which are the zinc chloride cells. It's a modified zinc carbon cell. What is the modification? As I told you, in the primary carbon zinc dry cell, what you have is the electrolyte, which is ammonium chloride as well as zinc chloride. In the zinc chloride cell, it is mostly zinc chloride, like 99% zinc chloride with only 1% of ammonium chloride added. And the cell, it usually turns dry at the end of its useful life. It has little chance of liquid leakage because the cell, it consumes water along with the chemically active material. So whatever moistness is there, it is kind of consumed, and when the cell is used up, it is generally a dry one. Then you have mercury cells. We used to have mercury cells, but this has a zinc anode and a mercury compound as cathode, and a potassium or sodium hydroxide as electrolyte. But it is becoming obsolete. Why? Because obviously mercury is hazardous. So currently we try to reduce the amount of hazardous compounds in any kind of devices. So that's why in the mercury cells are getting more and more obsolete. And then you have the last variety, which is the silver oxide cell. It has a zinc anode, a silver oxide cathode, and potassium or sodium hydroxide as electrolyte. And they are typically available. The voltage is around 1.5 volts. You have the button forms. They are generally used in cameras, watches, hearing aids. The type of cell which you see is basically nothing but your silver oxide cells. Then comes the rechargeable batteries, and here the workhorse for many years has been the lead acid wet cell. So this basically has a positive electrode which has lead peroxide, and the negative electrode is made of spongy lead. Electrolyte is sulfuric acid. Output is around 2.1 volts, and they are generally used either in series combination of 3. So it has a 6-volt battery, or you have a 12-volt battery. And these batteries normally, if you remember, we used to see it in all those different electric vehicles. This is one of the cells which is still being used. So the secondary battery, so what happens during discharge for this particular lead acid wet cell is the lead and lead dioxide reacts with the sulfuric acid and gives you lead sulfate with the release of water. While charging, it is just the reverse. And the current rating of these lead acid batteries, they tell you actually how much discharge current they can supply for a particular amount of time. And the unit is generally ampere hours. And the rating is, if you are having a higher ampere hour, the size of the battery is also larger. So the rating is proportional to the physical size of this particular battery. Specific gravity of a lead acid wet cell is very important, because when you actually measure the specific gravity of this particular cell, you will get to know what is the extent of discharge which has happened. Because as I told you, as you saw in the previous slide, that when the discharge is happening, it is leading to the production of water and lead sulfate. So as the amount of water increases, then lowering of the specific gravity of the electrolyte happens. And by checking the specific gravity, you can actually say how much of the cell, or how much of the cell has discharged, or how much charge is still left in that particular lead acid wet cell. So this is basically the same thing, whatever I have discussed in the earlier. So now another cell which we'll discuss, which is a rechargeable cell, is the nickel cadmium cell. This actually delivers a very high current. It can be recharged also many times. It can be stored for a very long period of time. And the applications are basically in alarm systems, in portable radio, in TV equipment. So you have nickel hydroxide, which is reacting with cadmium during discharge, giving you nickel hydroxide and cadmium hydroxide. The electrolyte is potassium hydroxide, but it basically doesn't take part in the reaction. It is only helping in conducting, the hydroxyl ions. So the potassium hydroxide is not a part of the chemical reaction which is taking place. Then what we have is a nickel metal hydride cell. So nickel metal hydride is nothing. It is similar to the nickel cadmium cells, but instead of cadmium, which is more toxic, what you have is metal hydrides. So it offers 40% more capacity over a comparably sized nickel cadmium cell. The negative electrode obviously is a metal hydride. This is more expensive than nickel cadmium, but it self-discharges also more rapidly. And it cannot be cycled as frequently as nickel cadmium cell, but still it is gaining more and more importance because of the toxicity which is associated with cadmium disclosure. Now, series and parallel connected cells, I'll just give you an idea why it is important, because when you're having particular cells, you're having a voltage associated with it. So what happens for a particular device if you need more voltage? What you do is generally you connect all these particular cells in series. Whereas suppose in some device you need to put in a lot of current. So for that current, what you have to do is you have to connect the particular cells in parallel combination. So it will have more current capacity, but the voltage is going to stay the same. So whenever you need more voltage, then you have to connect these particular cells in series. When you need more current, you have to connect them parallel. So this is basically how it is generally connected in series. You can see over here, and what are the notations. I'm sure everybody is aware of it. This is how it should look. So you have your voltage shown over here. You have the resistance and what is the current flowing through this particular circuit. This is how the schematic of a circuit diagram generally looks. So these are all the different examples which are given later on. If you are going through this particular lecture slide, which will be available, you can go through it and you can see how the series and different parallel connections occur. This I will not discuss in the class right now. So if you see, if you need more voltage as well as more current, then you will generally put in all these cells in combination of series as well as parallel connections. So that you can do the maths and you can connect all these different cells. And this actually will lead to your battery. Now the current which comes in, the actual amount of current which is produced in a battery, it is basically dependent on the load resistance it is connected to. So suppose we have a voltage of 1.5 volt and a resistance of 7.5 ohms. So in this case, the actual amount of current which will be produced by this circuit is 200 milliamperes. Whereas if you are kind of increasing your resistance to 150 ohms, then the same circuit is going to give you 10 milliamperes of current. And this is kind of determined by Ohm's law, where I is equal to V by R. So now coming to why batteries. Batteries, as you know, in 2019, the Chemistry Nobel Prize, it went to three very eminent scientists, John B. Goodenough, Stanley Whittingham, and Akira Yoshino. They actually won the Chemistry Nobel Prize in 2019. And according to the Nobel Foundation, the citation states that this lightweight, rechargeable, and powerful battery is now used in everything from mobile phones to laptops and electric vehicles. It can also store significant amount of energy from solar and wind power, making it possible a fossil fuel-free society. So it was a long-awaited Nobel Prize, which ultimately came in 2019, because as we all know that lithium-ion batteries have completely changed the way we function. We cannot think of a life before the LIBs came into the picture. So currently, if you see in 2013, in 2023, basically what we have is this is a $1 billion industry or $18 billion industry, and this is going to increase, to around it's a $31 billion industry, which it was in 2019, and by 2023 it will go up to more than double the amount. So this is the kind of technological impact lithium-ion batteries has had. So how does the lithium-ion battery work? So what is happening in a lithium-ion battery? The lithium-ion is shuttling between a host, which is your anode, and which is at a higher chemical potential. And then you have something which is the cathode, which is at a lower chemical potential. So in the lithium battery, see, there's a lot of confusion. In lithium-ion battery, the lithium-ion is shuttling between the anode and the cathode. In case of a lithium battery, the anode is nothing but your lithium metal. In a lithium-ion battery, the anode is basically currently the commercial lithium-ion batteries, the anode which is used is generally graphite. Whereas when we talk about a lithium battery per se, the anode is lithium metal. So what was the contribution of Stan Whittingham for obtaining the Nobel Prize? So basically what he showed way back in 1976 is that if you're having a lithium metal as anode and you have a cathode which is nothing but titanium sulfide, then what happens is that you're having a kind of electric current flow which is from the anode to the cathode. So the lithium is moving from the anode to the cathode, and what you are generating is basically a 3R LiTiS2 structure. So this was the first evidence of basically a reaction which is happening, and it is kind of in a very small, constrained space. It is actually giving rise to some electron movement. But this was a very unstable reaction. It was very unstable. There was a lot of instability here, and it led to the growth of lithium whiskers, and this would cause the battery to explode. What happens when a lithium whisker grows? So basically, you will have the growth of lithium. It will perforate this particular separator. It will go and touch the cathode. There's a short circuit, and then the battery is going to explode. But this was the pioneering work which actually gave an idea that, okay, with this, basically, an electron movement can be seen. So now coming to the contribution of John Goodenough. So John Goodenough, the previous work by Whittingham was in 1976. In 1980, what Whittingham came up was that we can have a lithium metal anode, but why don't we have some lithium metal in the cathode also? So what happens is basically he had used lithium cobalt oxide as the cathode, and he showed that yes, with this also, this particular material can work. So he developed the cathode. The concept was developed by Whittingham, and the cathode material, that is LiCO2, was developed by John B. Goodenough. And the next contribution was by Akira Yoshino. And what he did is that lithium metal whisker formation is actually leading to the explosion in these batteries, and it is leading to a lot of instability. What he did is kept the cathode as lithium cobalt oxide, but he changed the anode. Instead of working with lithium metal anode, what he said is even a graphite is able to basically intercalate this particular lithium ions. So this was revolutionary because this improved the stability, and then basically this material to come up to device formation. So in 1991, lithium-ion battery was commercialized by Sony and Asahi Kasei Corporation, with Samsung SDI beginning the manufacture of lithium-ion batteries at their Korea plant in the year 2000. So basically then lithium-ion batteries was commercialized. So now how basically a lithium-ion battery cell functions? So you have over here an anode, which is nothing but generally right now in the commercial lithium-ion batteries, what you have is a graphite. And you have a cathode, which is lithium cobalt oxide. So when you are charging, what you are having is basically an electron flow from the cathode to the anode, whereas the lithium metal is moving from your lithium cobalt oxide to the graphite, whereas when you are discharging it, the opposite movement is happening. So you are having movement of lithium ion inside the non-aqueous electrolyte through the separator between the anode and the cathode, whereas in the external circuit, you are having the movement of the electrons. So generally, when we are talking about battery, we have two important parameters to check for, or for any electrochemical storage device. When we talk about, we have two important properties. One is the energy density, and the other is the power density. And this is beautifully generally expressed using some kind of thing which is known as the Dragonite plot. So what is this Dragonite plot? It is the plot which is used to compare the energy density of various energy storing devices. So on such a chart, the values of the specific energy, which is given in watt-hour per kg, they are plotted versus the specific power, which is given in watt-hour in watt per kg. So this is along the power density is along your x-axis, and along the energy density is along the y-axis. So here you will find on the basis of energy density and power density where these different electrochemical energy storage devices stand. So when you are talking about a lithium battery, it is somewhere here. So you can see this is the power density and the corresponding energy density of a lithium battery. Whereas if you talk about fuel cells, it has a very high energy density, but the power density is very low. Whereas if you move into capacitors, you will find the power density is very high, whereas the energy density is quite low. So conceptually, if you see what does the vertical axis tell you is how much energy is available per unit mass. Whereas the x-axis, it will tell you how quickly that energy can be delivered. So if you need to store the energy, then we talk about energy density. If you need to give the energy in short bursts, a high amount of energy in short bursts, then basically we talk about power density. So the amount of time during which a device can be operated at its rated power density is given as the ratio between the specific energy, that is the y-axis, and the specific power, which is the x-axis. So now what happens is, now these straight lines, whatever you see in the Dragonite plot, it is nothing but what you have is basically the time of the particular device, the time scale of that particular device. So since these are all in logarithmic scale, it is very easy from the Dragonite plot to actually see where exactly each of this device fits in and what is generally the time period or hours during which the device can be operated. So this is a very important plot which you should remember whenever you are talking about electrochemical energy storage. So now coming to voltage of a battery, we keep on talking about voltage of a battery. So how you determine the cell voltage of this battery? So now the cell voltage, when you talk about, it is determined by the compatibility of this entire system. It includes the anode, the cathode, as well as the electrolyte. Normally, theoretically, what is the voltage? It is the difference in the chemical potential between the anode and the cathode. This is the working voltage, or which is known as the open circuit voltage. So this VOC is given by mu A, which is the chemical potential of your anode, subtracted with the chemical potential of your cathode, and divided by E, which is the magnitude of electronic charge. So this is your VOC. Now the difference in Gibbs free energy for the reaction between the charge state and the discharge state of the battery is generally given by delta HR minus T delta S. So this is nothing but delta U plus P delta V minus T delta S for this particular reaction. Now if you see this delta S, it corresponds to the change in the vibrational and the configurational entropies of ion insertion and extraction. And these are generally very negligible because the order, if you see, is around 10 to the power minus 5 and 10 to the power minus 2 electron volt respectively. So this T delta S value you can neglect. So what you have left with is basically your delta V. This is the change in your potential. And this is your basically the change in your internal energy. So this change in internal energy is generally 2 to 3 electron volts. So the delta G value, if you see, is actually related to this delta V, and which is nothing but your potential. So the chemical potential is correlated with the partial molar quantity of Gibbs free energy. So the equilibrium voltage is given by this particular equation, where E is equal to minus delta G by Xj minus Xi F. Xj and Xi is the solid solubility limits of the intercalation reaction. So whenever the lithium is moving into your different sites, it is nothing but it is getting intercalated. So it is the solid solubility limit of this particular intercalation reaction. So now what happens? We talked about this open circuit voltage. So you would say that, okay, fine, let me now just increase the anode chemical potential, decrease the cathode chemical potential, and then you will get a VOC which can be used. So you can just permanently keep on increasing depending on the material, the voltage of your particular battery or your cell, but that is not to be. Why? Because this VOC is limited by the electrochemical window of your electrolyte. So if you look into this right-hand side figure, which is shown over here, this is your electrolyte, which has your highest occupied molecular orbit and your lowest unoccupied molecular orbit. So the anode and the cathode, it has to be selected in such a way that the anode chemical potential, it lies below the LUMO of your electrolyte, and your cathode chemical potential lies above the HOMO of the electrolyte. Why this is so? Because if it is not so, then there is going to be or your electrolyte is going to reduce on the anode, or it is going to get oxidized on the cathode. And if that happens, what happens is it will lead to the formation of SEI. So this is nothing but a passivating solid electrolyte interface film. So between your electrode and your electrolyte, you will have the formation of this solid electrolyte interface film. Now what happens is, normally SEI formation generally happens. It occurs. Because somehow with different materials, what happens is that the electrolyte do tend to get, a little bit, it degrades. And it leads to formation of SEI. And this formation has both some positive and some negative. So let's see what is the positive point. So SEI film, it permits the diffusion of the lithium ions through the film under a uniform electric field, and it reduces the overpotential and the concentration polarization, which we had discussed earlier. So the SEI can prevent the aggregation of the electrochemically active particles, and it maintains a uniform chemical composition at the electrode. So this is a very plus point. So it prevents the aggregation of your electrochemically active particles. So in case of graphite, if you are having that SEI formation, what it does, it prevents the exfoliation, the continuous exfoliation of graphite. So it kind of seals it. SEI forms and it seals it. But it is not impervious to your lithium-ion diffusion. So the lithium-ion diffusion, it continues. But what is the problem? The SEI film, it increases the internal resistance of the battery. And what happens when the SEI forms, a part of the lithium, whatever is there, from your LiCO2, a part of the lithium is going and it is depositing as SEI. And that lithium cannot again move back to your LiCO2. So what happens in this process is actually you are losing your lithium. So if you lose the lithium, then what happens? You lose power as well as you lose the capacity. So ultimately, the formation, if the SEI formation, so it is a kind of a trade-off. It kind of preserves the integrity of your electrode, but then it also increases the internal resistance of the battery. So you need the formation of an optimum amount of SEI. So what is the theoretical capacity of electrode materials? This is very important. We keep on talking about capacity of the materials which are used. So for a battery or for a cell, this electrode material, it needs to have some capacity. And this capacity is given by the equation as is shown over here. It is NF by 3.6 into M, where N is the number of reactive electrons. In case of lithium-ion battery, it is Li plus, giving you Li, so it is only one electron. You have F is obviously the Faraday constant, and M is nothing but the molar weight of your material, whatever you are using. So, smaller molecular weight, as you can see, and larger number for N, what it will do? It will improve the capacity, the theoretical capacity of your electrode material. So in advanced materials chemistry course, we are trying to find out what materials are, is going to be good for these kind of systems. So now you have certain points which you have to remember. One is basically you have to see when you are using any material as electrode or you're designing any material as electrode for a battery, it should have a smaller molecular weight and it should have more number of electrons which is being transferred during that electrochemical reaction. And when we talked about in the Dragonite plot, you remember energy density. So how you get the energy density of a battery? It is basically the specific capacity of the battery, as you can get from here, which is multiplied by the working voltage of the battery. Okay. So if we now move to what are the elements which are available for the design of new electrode materials. So here comes your knowledge, whatever I have now taught for the past 45 minutes. So this knowledge is now going to be applied for all these different things, whatever we have built up as the basic. So which elements are available for the design of new electrode materials? So as I said, lighter elements will be preferred because they will give you higher specific capacity. And for this, the first 4 periods of the periodic table, they throw up very good elements for that. Then transition metal oxides, as you saw in the LiCO2, this cobalt is nothing but a transition metal. So these transition metal oxides are also very good materials. Why? Because the transition metals, they generally have variable valence state and it facilitates more electron storing sites. Then few more factors which we'll discuss in detail in the coming slides. The electronegativity and ionization energy, which determines the type of bonds between the transition metal ions and ligands. That is also very important when we are designing good electrode materials for batteries. So few points which we generally consider, which will be considered good from the industrial point of view, from the practical application from the point of view, from commercial aspect, is natural abundance, lack of competition with other industrial applications, eco-friendly nature for processing usage as well as recycling, and low cost. So technologically, the electrode materials must offer a large reversible storage capacity at a desired electrochemical potential. So now if you have a lithium anode, the theoretical capacity with that equation, if you calculate, you will find out it is around 3,850 milliampere hour per gram. For silicon, it is around 4,200 milliampere hour per gram. If you are considering the compound which is formed is Li22Si4. In case of lithium with graphite, it is generally LiC6. So what are the factors which affect the electrochemical potential of electrons? As I said, that mu A minus mu C, that is giving you your actual VOC. So what are the factors which affect the electrochemical potential? One primary thing is electronegativity. What is electronegativity? It describes the tendency of an atom or a functional group to attract the electron towards itself. So if you have a lot of difference in the electronegativity, it leads to the formation of an ionic bond. Whereas if the difference in electronegativity between these participating atoms which is less, then what you have is a covalent. So materials with ionic bonds, they generally form much more denser structures compared to what we get in case of covalent bonds. So this structural density, you have to remember, it influences the crystal or phase stability of materials, and it also affects the specific site energy of the lithium ions. And this can be correlated to the electrochemical potential of the materials. So electronegativity is one very important factor which you have to consider when you are taking into account how you can improve the electrochemical potential of your electrodes. Then, if you look into the potential and the number of d electrons, what you have in case of a transition metal, you will find that the potential is generally increasing as the number of d electrons keep increasing. So if you have a chromium, you have a manganese 4+, if you have Fe4+, CO4+, you will find that as the number of d electrons keep increasing, for the similar kind of material, whether it is lithium manganese oxide, lithium iron oxide, lithium cobalt oxide, or it is the simple oxides, you'll find the potential keeps increasing with the number of d electrons. Now, why this should be shown? Why it should be so? It is because you see, as you are moving from the left-hand side to the right-hand side of the periodic table across a particular period, what happens is the d electrons keep getting adding at the same level. So the screening of the d electrons, is very, very poor. The d orbital screening is very poor. So what happens is the outermost electrons is attracted more closely towards the area. So it's very difficult to remove or to add in electrons for this particular series. So when that happens, automatically, the more energy released when electrons are inserted into orbitals, or the more energy which is consumed when electrons are promoted from orbitals, the higher is going to be the electrochemical potential of the electronegativity. So this is the reason why when you have number of d electrons increasing, you find the potential is generally increasing. Then what happens that there are many other things also involved which can improve the electrochemical potential. So here I have given one example. See, look at bismuth and you look at molybdenum. You see mostly all the oxidation states of bismuth, they generally have a much higher potential versus lithium when you compare it with molybdenum. Why it is so? Because bismuth, it belongs to period 6 and group 5 of the periodic table. It has a large atomic number and a very large electronegativity. So it has a very high electrochemical potential. But a smaller gravimetric capacity. Look at the capacity. For bismuth, it is mostly, you find it is on the lower specific capacity compared to those of the molybdenum compounds. Why? Because molybdenum has a low electronegativity, but it also has a relatively lower atomic weight. So that is the reason why for molybdenum, you have a higher specific capacity, but you lose out on the potential, lose out on the voltage. So if you look into the average potential in phosphates, all these 3+, 4+ is basically phosphate materials. We have taken similar kind of phosphates and we have compared it. So the potential and the specific capacity is compared as phosphate matrix. So then the relationship, this particular graph is showing you the relationship between average potential of ion-based materials and electronegativity of polyanions. So instead of oxides, now you're having either phosphates or you're having molybdates or you're having sulfates. So what is the general trend you see over here? So as we are moving from lithium iron phosphate to lithium iron tungstate to lithium iron sulfate, what you see is the potential keeps on increasing. So with increasing electronegativity of the polyanionic group also, you find the electrochemical potential keeps increasing. So when you're selecting elements, the first step is the atomic weight consideration, its abundance, its environmental impact and cost. And then the electronegativity of the elements and the counter anions also is another key parameter which is going to determine the electrochemical potential of your electrode materials. So now let's see how basically for the lithium batteries, the material development took place. How basically all these different scientists, they thought to develop materials for lithium-ion batteries and whether we can learn about it. See this intercalation chemistry, because the entire thing is based on intercalation. Right? The lithium ion is moving from your LiCO2 cathode and it is going and intercalating in the graphite. So it is sitting in between the graphite sheets. So this intercalation chemistry involving reactions between a guest molecule or ion with solid host, this has been known for almost now 180 years. So Whittingham demonstrated, as I showed in the first paper of Whittingham, he demonstrated the first rechargeable lithium battery at Exxon Corporation in US with a TiS2 cathode and a lithium metal anode and a liquid electrolyte in which lithium salt like lithium chlorate was dissolved in an organic solvent, which is a Gleim solvent, and THF. What was the problem? Though it was the first demonstration of lithium batteries, but the cell voltage was limited. So obviously the energy density was very low. And then, as I explained to you before also, there was the dendrite growth of lithium metal anodes during cell cycling. So as the lithium anode, basically the lithium from the anode is moving to the cathode or getting intercalated to the titanium sulfide, what is happening in this continuous cycling process, when the lithium is going back from the TiS2 to the anode, it might go and sit on the same place over the anode. And so instead of actually spreading on the anode, it keeps on growing like a needle. And if that needle is growing very continuously, it keeps growing, then it perforates your separator, it goes and gets attached to the cathode, and the moment the anode and the cathode touches each other, there is a short circuit, and obviously there is internal shorting, there is fire has been present. So obviously, these were the problems which needed to be rectified. So now, then basically instead of the sulfide cathodes, oxide cathode came into the picture. And how did John B. Goodenough actually came into, instead of moving from sulfide, how he moved to oxide? That in itself is a very, very interesting story. You can actually see in a lot of Mantiram's papers, that entire history is given. It's a very fine read. I would suggest all of you to go and read it because I won't be able to discuss everything in short class of 1.5 hours. So the cell voltage is determined by energy difference between the redox energies of the anode and the cathode. And so the cathode energy, as you know, it should be as low as possible, and the anode energy should be as high as possible. So the cathode, what does this mean? So the cathode would require stabilization of high oxidation state with very low lying energy bands, whereas the anode would require stabilization plus the opposite, low oxidation states with a higher lying energy band. So now what was the problem? That how you can access this low lying energy band of a metal ion with high enough oxidation state so that the cell voltage can be increased. This was not possible using the sulfide cathodes. So Goodenough, he utilized the basic understanding that the top of a sulfide, this S2 minus 3p band, lies at a higher energy, as you can see over here, compared to the oxide. So this was remarkable. So this from very basic concept of chemistry, you see how a beautiful material was developed. So the access to low lying energy bands with higher oxidation states. So here you see cobalt 3 plus, cobalt 4 plus, if you see over here. With the oxide, actually you will be able to stabilize these particular states. But if you are taking a sulfide, then what is going to happen? This is going to basically result in an oxidation of this S2 minus to molecular disulfide ions, if you are using cobalt. So this cobalt higher oxidation states is easier to achieve using oxide kind of materials. So this was basically the idea, and immediately you see the moment they came into oxides, what was the, because this is your energy is considered with lithium or with graphite, you just see how the voltage immediately it increased. So where the voltage was around 2.5 volt when you are using TiS2, in this case the voltage moved up to almost 4 volts, and immediately the energy density showed a remarkable improvement. So using oxides, 3 different postdoctoral students in John B. Goodenough's lab developed 3 different kinds of oxide materials. So one was this layered lithium cobalt oxide, the other was spinel compounds, LiMn2O4, and the third was this polyanion or these lithium ion sulfates, molybdates, and tungstates, which was developed by Ryan. So this layered LiCO2 we have already kind of discussed. We'll discuss a little more later on. Then spinel LiMn2O4. In this case, what happens is lithium has two sides in a spinning compound. It has a tetrahedral and octahedral. In the octahedral, basically, the energy, if you see the voltage is around 3 volts. Whereas the moment it moves to a tetrahedral side, because of the presence of this Mn3 plus 4 plus couple, the voltage improves to around 4 volts. Whereas in case of polyanion oxide, it offered yet another way to increase the cell voltage by the inductive effect. The inductive effect actually again plays a role how the voltage can be increased. In case of iron oxide, the voltage is around 3.6 is around 2.5 volts. Whereas if you move to lithium iron sulfate, in that case, this voltage is increased to around 3.6 volts. So immediately the energy density of the battery increases. So cathode class 1, which was the layered oxide. So this is nothing but the structure of LiCO2. So what you have over here is monovalent lithium and trivalent cobalt ions. They are ordered in alternate 1-1-1 planes as shown over here in the Rockford structure with a cubic close-packed array of oxide ions, and this structure is generally known as a O3 structure. So the large charge and size difference between lithium and cobalt ions lead to good cation ordering, which is critical to support the two-dimensional lithium-ion diffusion and conductivity across this lithium plane. So with good cation ordering, what happens is this cobalt-cobalt interaction happens across the shared octahedral edges. As you can see over here, the cobalt-cobalt direct interaction happens. And so there is a very good electronic conductivity also, which is important. So lithium cobalt oxide becomes metallic on charging due to introduction of holes into the low spin cobalt 3 plus 4 plus. So ultimately it leads to the formation of a T2G6 minus X band. So the good structural stability along with high electrical as well as lithium ion conductivity, it offers fast charge discharge characteristics with a very good reversibility. So lithium cobalt oxide remains as one of the best cathodes to date with a high operating voltage of 4 V. But there is a problem for these oxides also, because the practical capacity of this material is limited to 140 milliampere hours per gram, though the theoretical capacity of this material is around 274 milliampere hours per gram. Now the reason is because if you are moving more amount of the lithium from this lithium cobalt oxide, what happens is there is a phase change. So it moves to the monoclinic phase, and whenever there is a phase change, then the stability of the electrode material gets compromised. So then basically the cyclability gets affected. So the practical capacity of lithium cobalt oxide is, that is the reason why it is kind of limited to 140 milliampere hours per gram. So now, because we had LiCO2, so then in this entire transition metal oxide first series, what are the materials which has this O3 layered structure? So we see that titanium has, vanadium also has that O3 structure, chromium has it, whereas cobalt, obviously we are using it, has it, and nickel also has it. But all of these cannot be used, they are not good cathode materials. All has been tested in various times in various labs by various scientists, and rich amount of literature has been generated. So what we have found out is lithium titanate, it operates at a lower voltage, and it is also very difficult to synthesize. Lithium LiCrO2, it is difficult to charge because it shows a lot of charge polarization with an increase in the charge voltage. And LiNiO2 is difficult to synthesize as a well-ordered material because in LiNiO2, what happens? Nickel should stay as 3 plus, right? But when you're synthesizing this material in a high temperature condition, then this Ni3 plus, it kinds of, it has a tendency to change to Ni2 plus. So when it does that, then in that case, it ultimately results in the formation of Li, which is having less than 1 minus Y, and Ni1 plus Y O2. So there is some volatilization of the lithium from this reaction mix. So it kind of gives some instability to the particular cathode material. Whereas when this M is vanadium and iron, the members, they suffer from layer to spinel transition or other structural changes during the charge-discharge process. So it's very important it doesn't undergo, these kind of structural changes. And this results because it has a very low octahedral site stabilization energy. As you can see over here, the octahedral site stabilization energy is much higher for a cobalt compared to that of a manganese. So that is why among this entire series, whatever can form this O3 layered structure, among them LiCuO2 is the best compound. So basically, good enough gives you the best compound in the layered oxides. So now, but if you look into the recent research which is happening in case of cathode materials, more and more emphasis is towards using Nmc cathode. What is an Nmc cathode? Basically, it is having cobalt, it is having manganese, and it is also having some nickel added to it. So each of these, apart from cobalt, we already know why. But why nickel and manganese is added? So in Nmc, what happens if you are adding little manganese? It tends to get oxides during synthesis to Mn4, and if you are having some nickel added to it, then that nickel Ni3 plus automatically gets converted to Ni2 plus. So without even playing around with without the chemical stability, manganese, it offers a lot of chemical stability into this Nmc cathode. Whereas if you see, the structural stability is provided by that of cobalt. And electrical conductivity, of course, is given by cobalt. And obviously, compared to cobalt, which is kind of the geological distribution of cobalt is very skewed in the Earth's crust, and the price is also very high. Cobalt mines are located in very specific locations in the world. So it gives, a technology which is going to be used by all and controlled by few is not a good situation. So if you want to use less and less amount of cobalt, and you can use more amount of nickel and manganese, which are kind of a little bit earth abundant, it is going to be more good for the later on the device technologies which are going to come. So that is why right now the emphasis on Nmc cathodes. So reducing cobalt content by adding nickel and manganese, what it does, it brings down the cost. It also improves the capacity. So in addition to the above two critical differences, cobalt 3 plus and 4 plus, it also becomes metallic on charging, as I had mentioned in the first slide when I showed you the LiCuO2 structure. So due to the partially filled T2G orbitals interacting along the shared edges, while Mn4 plus, it remains semiconducting. So Mn is abundant and environmentally benign, as I've already explained. And nickel, if you see the comparison of the characteristics, nickel, whether in chemical stability or structural stability or electrical conductivity, abundance, environmental benignity, if you consider all the factors, nickel lies in between manganese and cobalt. So nickel 3 plus and 4 plus band, it barely touches the top of the O2 minus 2p band. So nickel 3 plus, the advantage is it can charge all the way up to nickel 4 plus without removal of energy density from the oxide and loss of oxygen from the lattice. So that is a very important point. So obviously, it improves the capacity. And nickel 3 plus exhibits an octahedral site preference energy, which is intermediate between that of manganese 3 plus and cobalt 3 plus. So it offers reasonably good structural stability also. Hence, right now we are moving towards nickel-rich Nmc cathodes. Nickel-rich means what? The nickel amount is the highest. So you have something like 0.8 of nickel, 0.1 of manganese, and 0.1 of cobalt. So that is what we are currently moving towards. Lot of more research is happening so that we are having more and more nickel-rich cathodes. So then you might ask me, then why don't we go directly to LiNiO2? Why not use LiNiO2 for it? But that is a bit problem, as I had discussed earlier. It is difficult to have Ni3 plus in LiNiO2. Some amount of this Ni3 plus will try to get into Ni2 plus, and with that there is going to be volatilization of lithium, so that is not desirable. Then LiNiO2, it undergoes a series of phase transitions during the charge-discharge process. So if there is a deep charge involving the removal of a significant amount of lithium from the lattice, so this can again lead to degradation in the rate capability. Rate capability means that you are sometimes you are using higher current, sometimes you are using lower current rate. But in spite of that, your material actually, when you give low current rate, it again revives, and when you give high current rate, it gives you faster charge depletion. So all those factors needs to be considered when we are talking about batteries. And nickel 4 plus, again, the problem is it is highly oxidizing and it reacts aggressively with all the organic electrolytes. So it will lead to the formation of a very thick SCI layer, which is going to increase the electrical resistance of your battery. And if the electrical resistance is increasing a lot, then there is a problem which is happening with the rate capability as well as the capacity of your battery. So that is why we cannot use Ni-2, but what we do is we are synthesizing nickel-rich Nmc cathodes having a little bit of manganese, which stabilizes the Ni2 plus inside this Nmc cathodes. So each of these elements which has been added in the LiCO2 has a definite role to play. So now the push to increase the energy density, the potential to obtain higher capacity as Ni3 plus would be oxidized all the way to Ni4 plus, and the unsolvable problem of the voltage decay associated with lithium-rich layered oxides have reinvigorated the interest in high nickel content oxides during the past few years. So when we look into NMC cathode, is that the ultimate answer? No, because still we have a lot of problems to solve in this NMC cathodes. So here I have listed out a few. One is cycle instability, thermal instability, and also air instability. So these are all related to the instability of nickel 3 plus or nickel 4 plus in contact with your liquid organic electrolyte or ambient air. These are the different problems which needs to be solved, and various research groups all across the globe are currently working towards solving these different problems. How to improve cycle instability, how to improve thermal instability, and also air instability when you are using high nickel content in the NMC cathodes. So all these things I have already explained. So this I have given in the slides so that when you go through these slides, you can again have a better understanding of what I'll try to explain to you past 8 minutes. Now, as I said, that a lot of different labs are working on different improvisation. So one of the improvisation which is showing a lot of promise is basically the development of bulk cation doping in this NMC cathodes. So this bulk cation doping as well as surface stabilization strategies, which minimizes the volume changes, crack formation, and surface reactivity, which can help overcome this various instability which is associated with the NMC cathodes. So if you substitute this transition metal ions with a small amount of, if you look over here, instead of these transition metal ions, at some position you are having this aluminium coming in. So you are doing some amount of aluminium doping in this NMC. Then what happens? It makes the lattice robust by perturbing the long-range metal-metal interaction, whatever you see over here, and increasing the metal-oxygen bond strength. And so it suppresses the metal-ion dissolution. So because aluminium, it has been found that a lot of metal-ion doping has been studied, but it has been found that aluminium, it drastically suppresses the metal-ion dissolution from the cathode. As the covalent bonds keep the oxygen tightly bonded, lowers the basicity and discourage these kind of metal ion dissolution by acidity. So this NCME cathodes, nothing but NMC cathodes, very little amount of aluminum has been doped currently. The research flavor of the season, you can say. So now coming to the class 2, which is basically the spinel oxides. In the spinel oxides, what is happening? The Mn3 plus and 4 plus ion, they occupy something which is in the 16D octahedral sites, whereas the lithium ion occupies the 8A tetrahedral sites in the spinel framework. And this has a cubic close-pack array of oxide pairs, as you can see over here. So ultimately, what you have over here is a direct MN-MN interaction across the MnO6 octahedral edges. Similar to that as you find in LiCO2, so the electronic conductivity for this particular material is also quite high. And what it has, if you look into, this structure you will not be able to make out, but I have given a rotated view. You can see how basically the lithium ion is arranged. And this provides a channel for the movement of the lithium ions. So the lithium insertion and extraction from the tetrahedral sites offers a higher operating voltage of 4 volt, and the practical capacity is less than 130 milliampere per hour grams, which is as close to the 2 Mn ions. It can be reversibly extracted from the tetrahedral sites. So basically what we get from this particular material is a voltage of around 4 volt, and a practical capacity of around 130 milliampere hour per unit. But what is the advantage compared to LiCO2? Here you are having something which is earth abandoned. Because as I told you, over there the capacity was around 140. Here it is 130. So then obviously the question will come, then why this? Why not that? Obviously the reason is because this is a much earth abundant material, manganese, compared to that of cobalt. So lithium diffusion, if you see, in case of LiCO2, it is a two-dimensional lithium diffusion from one octahedral site to another octahedral site in the lithium plane. Whereas in case of your spinel cathodes, it is a three-dimensional lithium diffusion from one 8A tetrahedral site to another 8A tetrahedral site through a neighboring empty 16C octahedral site. So a 16C octahedral site is empty and it moves from one tetrahedral site to another tetrahedral site through this vacant octahedral site. So it is a three-dimensional movement, whereas in case of LiCO2 or the layered oxide, it has a two-dimensional movement or a diffusion. So what is the problem with the spinel oxide again? Because everything cannot be good. So there is a dissolution of manganese from the lattice into the electrolyte. If you have trace amounts of acid present in the electrolyte, because there is a disproportionation of manganese 3+ to 4+ and 2+ in acid. So when such a disproportionation occurs, what happens? Manganese 4+ is retained in the solid, but manganese 2+ is leached out into the solution. And if this manganese 2+ goes and deposits into the graphite anode, it kind of leads to a poisoning, and your cell gets completely degraded. So what is the step to circumvent this? So it has been found out that if you're substituting a small amount of lithium for manganese in LiMn2O4, then it perturbs this long-range MnM interaction or contact, and it frustrates this Mn3+ disproportionation reaction, and so the kind of this the stability of this material increases. So again, for LiMn2O4 also, wherever the spinel is possible for these different scandium, titanium, vanadium, chromium, manganese, iron. So you will find out that whether these oxides can also be used as cathode material. But it has been found out that LiMn2O4 is the best choice because the others which do form spinel compounds and don't undergo phase transformation during charge-discharge process, among these the Ti2O4, it operates around 1.5 volt, which is way too less, so it is not a suitable cathode. And the vanadic one, it suffers from structural changes and a lower voltage. The voltage for LiMn2O4 is around 4 volt, which is apt for a good electric density, good energy density. So the last class of the cathodes, which is the polyanion cathode. So as I had already discussed with you, see, if you look into the potential, lithium-ion potential is 0. So when I look into the cathodes, when I'm talking about Fe2+, 3+, if you look into the potential over here, and for the ferric molybdates and the ferric sulfates, what you find is basically the potential difference kind of increases. So for Fe2O3, it is 2.5 volt. When it goes to molybdate, it is 3 volt, and when it is sulfate, it goes up to around 3.6 volt. So what happens? In these kind of materials, you have FeO6 octahedral, and they share their corners with this kind of XO4, or this is MOO4 or WO4 or SO4 tetrahedra. And what it has is an extensive three-dimensional linkage of O, FeO, XO, FeO. So this type of linkage is there. So the more covalent this MOO or this tungsten oxygen or the sulfur oxygen bond it weakens, because it is more covalent, the FeO bond covalency through inductive effect compared to that in a simple ion oxide. So what we are having over here, this is more covalent, so it weakens this bond covalence. So it results in the lowering of this Fe2+, Fe3+, redox energy, and consequently the operating voltage it increases. The moment operating voltage increases, please remember, your energy density is nothing but a combination of your theoretical capacity or the capacity which is delivered by the electrode material multiplied by the voltage. And so if the voltage is increasing, the operating voltage is increasing, the energy density is increasing. So this is how basically these three different class of materials got developed. So this is again the same thing in a different diagram which I'm showing you over here. So as you can see, when you're having a ferric sulfate kind of material and a ferric molybdate, What you have over here is your working voltage, which is 3 volt in case of a molybdenum, whereas it is 3.6 volt in case of a sulfate, and this is due to the higher inductive effect. So with this, different types of all these inductive effect came into the picture, and ultimately in 1997, it led to the development of another very important class of cathode material, which is LiFePO4. LiCO2, obviously, because of the higher cost of cobalt and the less availability of cobalt. LiFePO4 is considered to be a very good choice because the voltage can be increased very high to almost 5 volt, though we cannot really go up to 5 volt because the electrolyte is the hindrance over here, because electrolyte dissolution takes place, electrolyte degrades. We don't have an electrolyte which can actually support 5 volt as of now. Only in research level we are having this kind of electrolytes, but nothing which has come up commercially. So these kind of the ability to increase the voltage drastically to as high as 5 volt in polyanion cathodes, like in this LiCO-PO4 or LiNiCO4. So this inductive effect, basically, it kind of increases this operating voltage. So currently, a little bit of work, currently a lot of work has been done with LiFePO4, but with this LiNiPO4 kind of materials, work is going on in the lab level, but as I told you, the point of constraint is basically the electrolyte. So all these different polyanion oxides like vanadium phosphate, sodium vanadium phosphate, sodium vanadium oxyphosphates, they have all been developed, which are kind of alkaline cathodes for lithium-ion batteries. The sodium ones are also good for sodium-ion batteries, but we are not covering sodium-ion batteries in this course. But please know that sodium-ion batteries are also in the foray right now. They are on the verge of commercialization. So that is also another alkaline battery, which will very soon come to the market. So what are the advantages and disadvantages of the oxide cathodes? So let's see, layered and spinel oxides, they have very good electronic conductivity. They have a closed packed structure with very high density. They have very high volumetric density. Whereas the polyanion oxides, they suffer from a few disadvantages. They have poor electronic conductivity. They have lower density. They have low volumetric density. But they offer an important advantage also, polyanion oxide, because they have very high thermal stability and better safety than the layered and the spinel oxide. Because in these cathodes, the oxygen is tightly bound to the phosphorus, sulfur, silicon with very strong covalent bonds. So the safety aspect is much higher for a polyanion oxide cathode. And small particles, if you are using which is coated with carbon, it can sustain high charge discharge rate due to very good structural integrity. Though the volumetric energy density is low. So if you are having a low volumetric energy density, rather than using in applications like, volumetric energy density means what? For the same amount of density, you have to use a larger size. So obviously you cannot use these kind of things for a portable device, but obviously it can be used for, energy storage for renewable energy. So you have wind energy, solar energy, these are intermittent supply. You need to store it. So rather than using lithium-ion batteries for that purpose, with lithium cobalt oxide as the cathode material or the spinners as cathode material, you can use this LiFePO4 as cathode materials for those kind of applications. And for your vehicles, for your electric vehicles, you can use the other normal cathode materials which you are using. So if you look into the energy utilization chain, there are three important points. One is harvest, the other is storage, and the other is management. So harvest and conversion of sustainable clean energy, which is right now we look into fossil-free world with solar energy, fossil fuel-free world. So right now we are looking into solar energy, wind, mechanical vibration, waste heat. So we are improving energy storage in the form of chemical potential, including batteries, hydrogen, biofuel, and management and efficient usage of energy with smart buildings and efficient energy systems. So why batteries are, the lithium-ion battery technology is not showing any sign of decline. Continuous work is going on. Why? Because right now, again, there is a lot of emphasis on electric vehicles. Why electric vehicles? We all know, improve air quality, because the vehicle emissions are high. Then you have greenhouse gas emissions, which are far less compared to the internal combustion engine vehicles. Then you have superior technologies, reduced operational and maintenance costs. So that is why currently, rather than from ICE EV, we are more and more, we are looking forward to electric vehicles. So if you look into the brief history of electric vehicles, the first was made at around 1890, became very popular in 1900s, but then when fossil fuel came in, then it kind of completely wiped out the electric vehicles. Then again, fossil fuel shortage started in 1970s, and then there was again an interest generated in electric vehicles. In 1990s, the Environmental Energy Pact came in, so there was new requirements on emissions. 1997, Toyota, it introduced the Prius hybrid. And in 2006, Tesla began producing all-electric sports cars. So currently, if you see, from the lead-acid batteries which were being used to nickel metal hydride batteries in the vehicles, currently it is lithium-ion batteries. They are the fastest growing battery system. Lithium-ion is used where high energy density and lightweight are of prime importance. And what you have energy density of 100 to 265 watt-hour per kg. The maintenance requirement as of now is not very much. And lithium-based batteries, they continue to improve, as you can see from this particular Dragonite plot which is shown over here. So there is a cost parity coming in. Cost is definitely a factor, but every year we find the cost is reducing. So this is the cusp here. You can see in 2024 to 26, this is what has been predicted, that it is going to be almost same price as that of an ICE. So currently what we have, Tesla has the top speed of 125 miles per hour. Acceleration is 0 to 60 in 3.7 seconds. The range is 244 miles and the price is $110,000. So that is the reason why batteries, if you look into functional materials, batteries definitely is one of the research areas which is going to gain prominence in the coming many years. Lot of different types of batteries. In this particular course, we are talking about lithium-ion batteries, but many alternate technologies in the battery, which is electrochemical energy storage, is coming into the picture. And yes, electrochemical energy storage definitely seems to be the call of the future, as well as the present. So with this, today I will conclude the lecture. In the next lecture, again, we will continue with how exactly you go about getting the materials and what exactly, how you work about in developing a battery. What are the different techniques, experimental techniques you will use to find out whether the material whichever you have developed is good or not. So all those things we will discuss in the next lecture. So if there are any questions, I'm ready to take them now. So, okay, fine. So I know it has been a very long class, and so what I would suggest to all the students who had participated, please go through the slides, and if you have any questions, we'll take it up in the next class. With that, I would like to end the lecture. A very good evening to you all, and to all those who will be listening to this lecture online or viewing it online later on, a very good day to you. Thank you very much.